Dear student, let us begin the lectures on machine design part 1. This is lecture number 24 and the topic is design of welded joints, and this is the concluding part of the lecture on the same topic. Let us recapitulate a little bit what we had learned in the last class. We talked about different kinds of the welded joints, different types of welding processes, and towards the end we mentioned about the strength or the factors affecting the strength of these joints. Now let us begin from the same place where we had ended in the last class. So this was the strength of welded joints we are talking of. Now the strength of welded joint gets affected by, there are few criteria, few things which affect the strength of the welded joint. One is the crack initiation. Now we mentioned that there are few causes of crack initiations, that may be due to the solidification contractions. Then there may be the cracks in the heat affected zone. Then there may be cracks due to the residual stress or incomplete penetrations, etc. So there are various reasons for crack initiations. Then we talked of the residual stress. Now because of the inhomogeneous or non-uniform heating of the weldment, that is the parts which are to be joined by welding, because of the non-uniform heating sometimes we get the stress, and this stress is very dangerous because they may lead to the cracks, as I have told just now. Then metallurgical transformation may take place. Near the heat affecting zone has the grain size becomes coarser because of the heating, and that makes the strength low. So therefore the strength gets affected in the heat affecting zone due to the metallurgical transformations. There may be various defects possible, that is because now welding could be considered to be a solidification or casting process. Now all the defects present in the casting process will be present in the welding as well. So there may be incomplete penetration, there may be porosity, and there may be slack inclusions or foreign element inclusions, which may also reduce the strength of the joint. And last but not the least, the stress concentrations. The stress, there may be certain some regions where the stress may be concentrated. So this will lead to failure if proper care is not taken. Now these are about the strength of welded joints. Now let us look. Let us now start the design of welded joint. Now for the sake of discussions, we have classified the design into broadly two parts. One is design for static loading and design for variable loading. Now any joint is meant not only to carry static loading, but some amount of dynamic loading also. In machinery, the presence of dynamic loading is very obvious because there are various movable parts, and because of the movable parts the force may be fluctuating. So the variable loading is also very important. For the static loading, we discuss in two the two cases, the butt joint and the fillet joint. Now again, fillet joint may be of two types. One is parallel fillet weld, one is transverse fillet weld. We also discuss how to design a welded joint which carries the torsional load, that is the torsional stress will be taken by this joint. So this is what will be the subject matter today, the design of static loading and the design for variable loading. Now let us come to the design of butt welded joint for static loading. Here if you remember butt welded joint, so there are two metal pieces which are to be connected by means of welding. So we introduce weld material here. So, this is the welded material. Now, this joint has to carry some load. It carries a load, let us say P. Now, definitely the maximum value of P will be governed by the tensile strength of this joint member. So, the tensile strength, that is sigma is equal to P divided by, now the cross section area, definitely the cross section area is this one, H, times the width of the plate or the length of the plate, H L, and that must be less than equal to sigma allowable. Now, this is the design criteria. We in design we want, or we want the joint to carry certain load P. We select L and we know sigma allowable. From this value we design what is H. So, this is the general design procedure. Now, this butt joint is now taking any longitudinal axial load. Now, suppose it wants to take transverse load. So, here instead we take transverse load P, then definitely there will be the average shear stress. Then tau is tau average will be P divided by H times again L, and that must be less than tau allowable. Now, here this is the average stress. Now, we can find out the tau max if the cross sectional area is rectangular, then we can get a tau max which is roughly equal to 1.5 times tau average. So, from this data we can design what will be the H of the fillet, or H of the butt welded joint, or sometimes L, or maybe sometimes P max, etc. Now, this is a square butt, as you remember from the last lecture, that there are various kinds of butt joints. Now, if you talk of different kinds of butt joint, then what you get, so this is, let us consider double U or J type butt joints, let us say double U. Here this is the two, these are the two parts to be mated, and we insert weld melt here. So, now the effective cross section is now reduced by some amount. Let us consider the same P axial load. Now, the effective cross section is, now if this distance is H1 and this distance is H2, that is this part does not carry any load, this one. So, therefore, sigma will be equal to P divided by H1 plus H2 times L, and that must be less than equal to sigma allowable. So, this is the design consideration of the butt welded joint. Now, it is very simple, the butt welded joint. Now, when we come to the complicated case, then we see the complication arises because of the typical shape of the weldment. Let us now go to the next topic, that is the design of fillet welded joint. Now, we consider the parallel fillet. If you remember, parallel fillets Now, here it carries a load P. Now, parallel fillet is the fillet which is applied here, that is the welding is done in these two places. This is longitudinal fillet or parallel fillet. Now, what will be the design criteria for that? So, if you look from this side, then it looks like there are two plates like this, and then the fillet joint. This is the fillet joint. Now, it carries a load P. So, the P is acting over here and there in two opposite directions. The pointing the arrow here, the direction is towards the reader or away from the reader. Now, if you want to design for the strength, then what you have to consider the cross section where the joint is maximum vulnerable, and that is clearly the cross section here. It can be further elaborated with the help of a similar diagram. Now, here is that fillet. Now, definitely the vulnerable cross section is here where the area is the least. So, this is now the part which is seen from that side, and this is the three dimensional view, and there, and definitely when you look at the fillet, then this is pi by 4, it is roughly of the same height and leg length is same. So, therefore, this length which is called the throat, then T will be equal to H by root 2, as you may verify. So, therefore, the maximum shear stress here will be equal to, now it has to fail in shear. So, we will have to consider shear stress, because this material is such that it fails in shear full mode. So, therefore, we will have to consider the shear stress. Now, the maximum shear stress will be equal to definitely tau max will be equal to force divided by total cross section area, and here the total cross section area is T times the length here, length, and there are two such welds which are symmetric. So, therefore, twice T L, and T from this earlier relationship we can get, that is equal to, that is this part will be equal to tau max is equal to root 2 by 2 P by H L. Now, this is the formula which we use for designing the parallel fillet in the fillet welded joint. Now, what you see here, this is symmetrically placed, that is the all these two lanes of the weld are same in both sides. Had it not been so, that is, if we had welded only in one place, let us consider that, suppose we had welded only along one place, then what we get is there will be a bending stress developed. Now, in this case asymmetry occurs and there will be bending stress developed. So, there will be bending stress due to asymmetry. and that is what we do not want, because if we have bending stress, then that may be very, very large, because the cross section area and the rigidity, the modulus, say sectional modulus is so small that the bending stress becomes very, very large, and the material may fail or the joint may fail. So, therefore, we want to avoid that. We want the joint to be symmetric, that is, we do not want any bending stress to be developed in the weld joint. But suppose we have the structure, that is the plate, that is the plates which are to be joined, if they have the asymmetric geometry. That is, now we consider a case where there may be asymmetry here. So, if you look from this side, the joint suppose looks like suppose we have L joint, something like that. So, this is the cross section of the plate. So, this plate cross section is here. We have the center of gravity somewhere here. So, this is the center of gravity, and now if you apply the similar joints in both sides, again because of the asymmetry of the structure, there will be bending stress developed. So, we will have to make two different lanes of the welding now. So, now we have to make so this will have length L1 and this will be of length L2, let us say, and L1 and L2 are not equal, and this axis is the axis of the geometry of this center of gravity of this cross sections. Then the first condition is that the forces taken by the weld, if they are considered to be F1 and F2, that is F1 plus F2 must be equal to P, which was applied there. So, this was P and this was P, and here we have the force taken by this weld F1 and F2. If you consider this distance, that is welds are applied here and there. Now, if you consider this distance, let us say this is E1, eccentricity 1 and E2. Now, we want the welds not to be affected by any bending stress. So, now we have to select L1 and L2 such a way that the resultant F1 and F2 pass through the applications of P, and normally we apply the load which passes through the centroid, the sectional centroid of this member. So, now we have another conditions, that is, if you take moment about this axis, it will be F1 times E1 will be equal to F2 times E2. Again we have this relationship, that is E1 plus E2 will be equal to total height H is H, and then we see that F1 and F2 have these relations, that is, if you now see that we have F1 by E2 is F2 by E1, and that is equal to F1 by plus F2 divided by E1 plus E2. So, this is equal to P divided by H. Now, we select F1 to be E2 times P by H, and F1 will be equal to the maximum load taken will be equal to tau allowable times root 2 divided divided by the area times the area of cross section, and this area of cross section is equal to so this area will be equal to T times L1, and T is, if the leg length is S, then it will be equal to 1 upon root 2 S L1, where S is the length, the of fillet. So, from this relationship we calculate the value of L1 and similarly the value of L2. So, this is how the design is to be made. I emphasize here, I stress again that the designs must be so that the welded joints do not experience any bending stress. So, this is very important, because bending stress is very detrimental for the joint efficiency, or it leads to the joint failure. So, this thing must be remembered very well. Now, this was about the parallel fillet joint. We are now going to come to the transverse fillet joint. So, we are now going to come to the transverse fillet joint, which is, of course, it is known. How does the transverse joint look like? Again, we have similar configuration. We have, let us say, force P, and here we have P, and the transverse joint, here the welding is made here. Now, here the analysis becomes quite complicated, as we will see very soon. We take the example of a double transverse fillet, that is a double fillet joint, where there will be two such plates. Now, if you look at the cross sections, it will be something like this is one plate, these are other two plates, and we apply a force to F here, this will be taken by as F and F, and the weldment is here and there. So, this is the welding. Now, if we use the strength of material approach, then we take a cut. We want to find out the average stress at any sections. We take a cut, let us say cut here, two symmetric sections which makes an angle theta. We take the cut and draw the free body diagram. The free body diagram will look like so. Now, we draw the free body diagram. This angle is theta, this angle is again theta, and there will be no force here, and there are these other forces, the normal force. Because of symmetry, there will be the same normal force there, and there will be the horizontal, that is the parallel force. Let us denote this by H. Now, if you write down this angle, then it becomes this angle. You see, this angle is theta, so therefore this angle becomes theta. And if you write down the equilibrium equations, then it becomes, the equilibrium equation becomes something like this, equating the vertical force, that is balancing Fy to be 0, we get n sin theta is H cosine theta, and equating the horizontal force to be 0, we get n cosine theta plus H sin theta, and there are two such things. So, therefore, twice will be equal to twice F. Now, if you just manipulate a little bit, what you get, if you substitute the value of n here, because we need both n and h, if you substitute the value of n, then what you get, is seen here, that is h, if you substitute the value of n, which is equal to h cosine theta by sin theta. So, therefore, cosine square theta by sin theta plus sin theta will be equal to f, and that gives h is equal to f sin theta. Now, and n will be equal to, n is given by the same formula, that is n by h is equal to cosine theta by sin theta. Therefore, m is cosine theta. So, this are solved. Now, we have to find out the area of cross sections. Here the area is the length times this length. So, that is the throat length, or I should not say throat, but the length here. So, let us denote this by T prime. What is that T prime? So, that comes directly from the if you consider the geometry. Let us consider in a little bit details. What we have there is if you consider this part, that is the fillet section, originally it was, this angle was pi by 4. Now, we have taken a cut at angle theta. So, therefore, this angle alpha will be equal to pi minus pi by 4 plus theta. And if you use the sine law of the triangle, here this height, this length h, this is h, if this is T prime, then we have the following relationship, that is T prime by sine pi by 4 is h by sine pi minus pi by 4 plus theta will be equal to pi by 4 plus theta. So, therefore, T prime will be equal to h by sin theta plus cosine theta. So, if you want to calculate now the maximum shear stress or normal stress across that sections, then you get the following relationship. What you get now is the normal stress will be equal to n divided by the area, that is T prime times L length. So, this is equal to, as I discuss, f cosine theta times sin theta plus cos theta divided by h L. You have tau is equal to f sin theta plus cosine theta divided by h times L. Sorry. Then from this relationship we can find out the von Mises stress. The von Mises stress will be equal to equivalent stress is mass square plus thrice tau square. The von Mises we can get tau is 1 upon root 3, the equivalent shear stress in the von Mises stress failure criteria. We can have tau max as well. From this relationship, if you know this tau here, then what you get tau max, first we will have to differentiate d tau d theta and that to be 0, then gives the relationship between theta which is equal to, you will see if you carry these calculations, then theta becomes 67.5 degree, and if you carry out this relation, then tau max you get, you substitute the value of theta in tau here and you get the maximum value of tau to be approximately equal to 1.207 f by h L. This is about the tau max, and if you calculate the same for the von Mises stress, that is the von Mises stress, again it appears in the same angle theta equal to 67.5 degree, and that becomes almost equal to 1.25 f by h L. So, this I leave to you to calculate that, but what is important is that having done all this stuff, what we get is the average value, but it seldom matches with the experimental results. Experiment was carried out with photoelastic apparatus, photoelastic experiment was done, and it was found that it is very difficult to find out any match, that is there is practically no match between the strength of material approach and the reality. So, after some discussions and many research, it was arrived that if we consider for the design purpose, if you consider the same thumb rule that the maximum chance of failure is near the throat, then the following relationship could be obtained, which is now here we consider that the maximum failure chance is at theta equal to 45 degree instead of 67.5 degree. But if we neglect the normal force on that particular sections, then what we get tau max is 1.414, this is square root of 2 f divided by h times L. Remember, h is the length of L is the length of the joint and h is the leg height of the fillet weld. Now, you will see that although this is a thumb rule, and here the assumption is that the stress is uniform over the cross section, making an angle theta equal to 45 degree, and we have neglected, if we neglect the the normal force on that particular sections, then we get tau max equal to this value, and this is of course greater than the tau max obtained here from the strength of material approach. So, this is tau max with strength of material approach, or maybe it is greater than even tau prime, which is the corresponding shear stress in the von Mises failure criteria. So, this is very very conservative result which we have for this transverse fillet. Now, this is normally used in practice. Okay. Now, here although this is almost a thumb rule, this is no way an accurate theoretical results, but of course, it is very very useful, and this is the unified formula which is it is called the unified formula. So, let me write down this formula again, which will be the basis of calculations for the strength of welded joint for a transverse fillet weld. So, we have this unified formula, that is tau equal to 1.414 times F divided by H times L, where H is the length and L is the total length of this weld. Now, this formula will be used, and this will be lesser than tau allowable. So, now what are the design criteria, design data? We want to have this joint which should carry the load F. We know tau allowable, we decide some value of L, and then we design the joint for particular H. So, this is the design parameter which we get from this following calculations. All right. So, this is about the design of fillet welded joint for the transverse fillet. Our next discussion is the design of fillet welded joint for torsional joint. That is, here we consider this is roughly the and the weldment is given here. So, here is the weld and torque is applied here. We want to design this welded joint. So, what will be the dimensions of this weld, this particular portion? Now, if you look closely into this joint, what you see here is the following. If you look there, but again we consider the most vulnerable area, and this is definitely this portion. So, therefore, the torque, the shear stress will be maximum over this surface. Then how to calculate the polar moment? You remember the formula, that is T, that is shear stress due to torsion, will be equal to T times C. If you consider the diameter to be D, then D by 2 divided by IP. Now, what will be the polar moment? Now, we want to find out this IP. Now, IP could be found out if you make some assumptions, and the assumption is that because compared to the diameter of this member, the thickness or the width of the welded joint, this welding is very small. So, therefore, if you consider the welding to be a line, now we consider this entire welding to be a line element. That is, the thickness is so small that we consider it to have almost no width at all. That is, now we have, if you look the cross section, then here the circle, now if you consider this inner diameter di and outer diameter do, and if you consider this to be very small, then di, if the thickness is, let us say, a, then do will be equal to di plus twice a. Now, if you calculate the polar moment, then the polar moment becomes IP will be equal to pi by 32 times do4 minus di4, and this, if you consider a to be very small, then this is all approximately equal to pi by 32 4 times d, let us say, I cube times twice a. So, that is approximately equal to pi by 4 d. Now, di, if this is very small, then do is almost equal to di, is called the average diameter. So, this is d cube times a. So, this is now the polar moment for this thin strip. Now, normally what is given in the table is the polar moment for per line. So, now we take a to be unity. So, what we get in the handbook is that we take IP to be, sometimes we call JP. Now, here if you consider this cross section, then what is now your A? A is nothing but the throat length, that is, A is T if you use the same connotations. Now, we know the shear stress due to torsion, which is equal to tau will be equal to T times d by 2 divided by pi by 4 d cube times T, and if you use the same notations, then this will be equal to T. So, this is twice T by pi d square times this is equal to h by root 2, and this is the shear stress due to torsion, and that must be less than equal to T allowable. So, we know how to design the fillet welds for a torsional member. For many other cases, you can find out the polar moments for a thin strip and then use the similar formula. Here again the assumption is that the stress will be, or the failure will be governed, or failure will be most probable in the throat area. So, here in the throat is that place where the stress gets maximum value, and we design from the throat according to the throat cross sectional area. Now, this is about the fillet welded joint for torsions. Let us look at the design stresses of weld made with mild steel electrode. Now, here the strength, because the analysis is very difficult for welded joint. So, we make lot of experiments, and with the help of those experiments we measure the strength of welded joints. Now, again the experiment in reality it will depend on not only the properties of the base metal, but also the properties of the weld metal, and it is the electrode which also affects what type of electrode. There may be bare electrode or may be covered electrode. Now, if we have a bare electrode, then the chance exists that there may be some contamination of oxygen, which may leads to embrittlement. If it is covered, then this chance is less. So, that is reflected here. You see, if you consider a butt weld, then the tension value here is 91.5, everything is megapascal, but the dynamic stress, now here we know that because of the fluctuating stress, the failure probability is more. So, when we have the dynamic load, then we will have to make the allowable stress quite low. So, that is taken care of by the fatigue stress concentration factor as well. So, if it is designed not to break, then we will have to have this endurance limit, which is sufficiently low compared to that of the static loading. Now, in tension we have 91.5, but in dynamic loading it is 35. If it is covered, then for the static loading it is 112.5, and for the dynamic loading it is 56.2. For the compression it is naturally quite large, it is larger compared to the tension. This is 105.4, and for the compression it is again 35, similar value. Now, here it is observed that for both compression and tension, if the loading is dynamic, then of course it makes no sense to talk of tension and compression if the loading is completely reversing, because in half the cycle it will be in tension, in half the cycle it will be in compression. So, they are equal in both cases. For the shear, again it is sufficiently low, and for the dynamic stress this is 21. For the covered electrode static stress it is 70.3, and for the dynamic load it is 35. For the fillet weld, normally we take only the shear, because fillet welds, as I have discussed in the last 2 or 3 design criteria, that we take the shear stress of the fillet into account, and shear stress is for the static loading 79.5, which you see it is large compared to that of the butt weld, but the dynamic stress is almost the same. For the covered electrode it is 98.5, again you see it is higher value than that of the butt weld, but the dynamic stress is the same. So, these are roughly the design stresses of welds. Now, we come to the fatigue stress concentration factor. Now, there may be stress concentrations. You see, if you consider a butt weld event, and if we have a weld here, so there may be a stress concentration because of the abrupt change in geometry. You see here the thickness is quite large compared to that. So, therefore, if you consider the force P here, the stress distribution will be somewhat like this. The stress concentration factor because of the abrupt change. Therefore, it is advisable to machine this off. We normally do not leave this as it is. One good practice will be to grind it. So, this is how we make this joint. Now, these are the this is one such case where the stress concentration occurs. There may be stress concentrations due to various other reasons. Suppose there is incomplete fillet. If you consider this case, that is suppose we have this fillet here. Now, you see, when we want to make two fillets here, then definitely there will be a gap, that cannot be avoided because of some error. So, this gap E, which is nothing but a crack if you consider the loading, that is, if you consider the real joint, then this is nothing but the crack. So, therefore, a stress concentration will exist over here. So, there is a large stress concentration here. So, these are there are various other possibilities of stress concentrations. Now, what you see here, the typical figures showing the fatigue stress concentration factor. Stress concentration is not that important for the static loading, but for fatigue load, for the dynamic loading, it is quite important. For the reinforced butt weld, it is 1.2. For the toe of fillet weld, this is 1.5. End of fillet weld 2.7, and T bar joint with sharp corners. Definitely we want to avoid the sharp corners, and it has a stress concentration factor 2. Now, there are various techniques to avoid the stress concentration factor. One is to make the leg size, that is the weld, that is the fillet weld, apparently unsymmetric. If you make this leg, this length much larger, this length much larger than that, then definitely has a gradual variation of the geometry, change in geometry. Therefore, the stress concentrations may be more. Then another technique is to make this contour concave, and that also reduces the stress concentrations. So, there are various techniques of stress concentrations removal. Now, let us come to the conclusions. What we have learned the different kinds of welded joints and how to design them. Now, designing is very difficult, and we use the thumb rule that it is only at the throat where the stress is maximum, and we design the welding from the considering only the throat cross sectional area. So, there are various literature available. If you read, if you have a chance to look at some of the textbooks, you will find many such design problems given, you solve them. Okay. So, this is as far as the welding joint is concerned, and I end here today. Thank you very much. This is lecture number 25, and the topic is design of joints with eccentric loading. Now, in last few lectures we have learned many facts, many ways how to design a joint. Now, these joints are of two types, non-permanent types and permanent types. For non-permanent types, we had the examples bolts, nuts, assembly, and for permanent types we had riveted joints or welded joints. Now, in all types of joints we have studied so far, we have used the load which passes directly through the center of gravity of the joint. Now, in many cases it happens that the load has some eccentricity from the center of gravity or the center of the joint. Now, what happens then? This is very, very important because lots of structures have this kind of loading. Name, for example, the tower crane, which has loading definitely eccentric. So, in those cases the eccentric loading of the joint is very important, and hence we will have to concentrate on the designing of such joints when we have eccentric loading. So, in this lecture we are going to study how to design a joint which has eccentric loading. Now, let us come to the joints which we have studied so far, and here in this lecture we are going to study how to design a joint when the joint is a riveted joint. You all remember what is a riveted joint, and it is a permanent type joint. The most of the applications where the riveted joints are used, the load is applied such a way that this riveted joint acts primarily under shear. So, this is the primary force, primary loading which is applied to the riveted joints. Sometimes it can take some tensile load, but normally we have the shear loading. Similarly, the bolted joints will normally take the tensile load, primarily tensile, and welded joints could be tensile or shear load. Now, here in this lecture we are going to study the eccentrically loaded riveted joints first, then how to design eccentrically loaded bolted joints, and last eccentrically loaded welded joints. So, now come to the design of eccentrically loaded riveted joints. Now, let us consider a riveted joint. Let us take, this is the structure. And we have a riveted joint. So, let us take, this is the joint, and then there are few rivets. Take for example, there are 4 rivets. These are 4 rivets, and we have a load which is passing over here. So, the eccentricity will be measured from the centroid of these 4 rivets, and that is given by this distance. So, this is the centroid, and this is E, the eccentricity of the loading. Now, you see what happens due to this